Let's do one more example. Oh, actually, no, that was work. Let's do an example of calculating Q. Now, you might remember from introductory chemistry, a Q is here C, which is heat capacity, capacity to hold heat. And here is a delta, means T final minus T initial. Here, lowercase c is the specific heat, which is the heat capacity per gram, and here m then would be mass. So this is typically a way you would use to calculate Q. You do a measurement, see how much the temperature changed, and multiply that by the heat capacity, or the heat capacity, the specific heat times mass, which gives you the heat capacity. Let's apply this equation to calculate Q for this example. This example actually is right out of introductory chemistry, but we'll review it anyway. I have a 7.5 gram piece of iron, and this at 100 degrees. And you drop that into 25 grams of water, 22 degrees. What is Q for the iron? The specific heat capacity of iron and water are this. Okay, so what is Q for the iron? Q for the iron, let's use this, will be the heat capacity times delta T. But we're not given final, and we're not given actually initial. Well, we're given the initial temperature of the iron, but not given the final temperature of the iron. So here we have to use calorimetry and first law concepts. All right, so let's do that. Oh, picture's worth 1,000 words. So here we're going to draw our universe. Our universe is the calorimeter. So if we go back here, ignore that. That's for the next example. All right, so let's look at this. Look at it this way. Here's the iron up here, and it is at 100 degrees C. Down here is water, and it is at, what would we say, 22 degrees. And here, I can't draw very well tonight, so let's try it again. Felt tip pen. So, and this is at 22 degrees C. And we said that this was 7.5 grams of iron, and this was 25 grams of water. Now note that there's a temperature gradient. Yes, there's a temperature gradient. So this is 100 degrees, this is 22 degrees, and so heat is going to flow from this temperature gradient. The iron is going to cool off, and the water is going to heat up. And let's make this insulated. So the only way the heat can flow is from the iron to the water. It can't get out of here. So let's try to figure out what's happening here. Well, we know that since this is insulated, the Q for the iron is equal to minus Q of the water. The heat lost by the iron is the heat gained by water. We're not doing any work. There's no expansion. So the energy change is just this Q that's transferred. And by the first law of thermodynamics, this is insulated, isolated system. Consider it. The heat lost here has to equal the heat gained here. All right, I should put the minus sign the other way. All right, so let's talk about the heat lost by iron, QFE. Well, that is equal to, from our previous equation here, let's see, we're given the specific heat capacity of iron. So we'll use this second form to calculate Q, mc delta T. mc delta T. So m is 7.5 gram. The specific heat given in the problem was 0.45 joule per gram Kelvin, 0.55 joule per gram Kelvin. And the delta T is the final temperature. We don't know what the final temperature is, minus the initial temperature, which was 100 degrees C. And similarly, Q for water, we'll use that again as mc delta T. We're going to use that form because we're given the specific heat capacity of water, 4.184 joule per gram per Kelvin. So we have 25 grams of water. The specific heat capacity is 4.184 joule per gram Kelvin. And here we have the final temperature minus the initial temperature, 22 degrees C. So we don't know what the final temperature is, but we do know what the initial temperature is. How do we calculate the final temperature? Well, let's put this here, and let's equate that to minus there, minus Q. So what we have is one equation, when we substitute these things in here, is one equation with one unknown. That's the final temperature. So I won't work it out here, but the final temperature comes out to be 22.5 degrees C. Now with the final temperature, we can go ahead and calculate Q for iron. Q for iron is the mass of iron, 7.5 gram, times the specific heat capacity of iron, which is 0.45 joule per gram per Kelvin. And the final temperature, 22.5 degrees C, minus the initial temperature of the iron was 100 degrees C. And this comes out to be 2.6 times 10 to the second joule. And note that this is a negative sign here, so it's minus. Now let me make that more clear here. Oh, I love the eraser feature. That's equal to minus 2.6 times 10 to the squared. And we expected a negative heat for iron because, again, our sign convention, we're sitting here in the iron. Q is negative because iron is losing heat. And similarly, Q for water will be positive. And in fact, Q for water will be exactly the negative of Q for iron. So Q for water will then be plus 2.6 times 10 squared joule, because Q is the only form of energy that's transferred, and it's an isolated or insulated container, and therefore the Q lost by the iron has to equal Q gained by the water. That's generally how you calculate Q. You have to know heat capacity or a specific heat times mass. Actually, let's go back here. Now you're probably wondering, here we have Kelvin, but here we have degrees C. So you're probably wondering what's going on here. Well, I'm going to claim that a delta T in Kelvin is equal to a delta T in degrees C. Let's convert, in fact, a degrees C to Kelvin. So we have, say T, I'll just use real units here, and real numbers. Okay, so suppose we have our temperature, first temperature, T1, is equal to, say, 25 degrees C, and say T2 is equal to 50 degrees C. So delta T in degrees C will be equal to the final temperature, 50 degrees C minus 25 degrees C, and that's 25 degrees C. Now let's convert all these temperatures to Kelvin. So let's do a delta T in Kelvin. Well, that will be 50 plus 273. So now we've converted this to Kelvin by adding 273, minus a final minus initial, minus 25 plus 273. That's in Kelvin. So this would be in Kelvin. But note that this would be 50 minus 25 plus 273 minus 273. So that will cancel out, and we'll just get 25 Kelvin. So a delta T in Kelvin is a delta T in degrees C. So that's why we used a degree C here in Kelvin. This delta here was the same 20, regardless of whether we used degree C or Kelvin. Okay, and that's that. And one other point I want to make here. Heat capacity, well, yeah, let's do it this way. So heat capacity C, that's heat capacity. If you take, and that has units of joule per Kelvin, as you may remember from introductory chemistry. Let's look at mass times lowercase c, which is specific heat capacity. I claim that m times lowercase c, specific heat capacity, is also a heat capacity. All right, so mass, let's express that in terms of gram. All right, specific heat is joule per gram Kelvin. So in fact, if you multiply mass times specific heat, you'll get joule per Kelvin, which is heat capacity. Right? So based on this unit argument, mass times specific heat is equal to heat capacity. Okay, so those are the extra points I wanted to make on this example.